So today, I'm glad to welcome you all to this first lunch talk of the new series on energy and mobility in transition. So we will organize a series of lunch talks that allows you to have an idea on how the transport and mobility sector can help and do their contribution in limiting the energy requirements of this sector. So today's talk will be by Stefan Bakker from the Knowledge Institute of Mobility in the Netherlands, and his talk will be about CO2 neutral energy chains for mobility. And before I will pass the floor to Stefan, I would like to also show you other activities that are coming up for the association. Of course, all the activities as well as presentation of today, they will be available on our website. I would also like to highlight that soon the BIVIC Gibet Transport Research Days will be popping up again. So in June next year, they will be held in person in Leuven by the colleagues from the KU Leuven. If you want to participate to this conference, you're able to submit your abstract, and the abstracts, they are due by the 15th of January. And then I also already want to make the advertisement of the next lunch talk, which will be held on December the 7th by Hans van Zeebroek from Fluvius. So with no further ado, I'm happy to pass the floor to Stefan.
Thank you very much, Mario, and welcome everyone. It's a pleasure for me to be in this event and present our work. We just tested how to share. Teams is a little bit new for me, so this is not the one that I want to share, I guess.
So if you, yes, the presentation is there.
Okay, is it
Perfectly visible?
All right, that is fine. It's always a challenge. Online presenting is, of course, a very different experience. But I'm happy to present some research we did in the past year together with my colleagues from the Netherlands Institute for Transport Policy Analysis. In Dutch, the abbreviation is KIM. This is an independent institute within the Ministry of Infrastructure and Water Management in the Netherlands, and we did this in collaboration with TNO. So this is quite a general, I mean, a very overview kind of research. We did it to really look into what are we talking about when we are looking at energy change for mobility. And we looked at 4 energy change: electricity, synthetic fuels, hydrogen, and biofuels. And we and included 5 modes of transport into that. And so also the combination of those energy change with those 5 modes of transport. And then we looked at 3 criteria: energy efficiency, costs, and land use. And this is mostly for the Netherlands, but I think many of the results will be in a certain way also applicable to other countries. The main aim of this study was to really look at recent information, really look at the facts, what is there in existing literature on the energy change, and contribute to, of course, to policy discussions, because the research that our institute does is always at the request of policymakers. So it's always directly relevant to policy. The ministry has a vision to work towards a mobility sector with 0 emissions in 2050. This is obviously a very big challenge. So we want to contribute to the question, how can we achieve this carbon neutral mobility on time? And there are many ways to look at that. It's a very big energy transition, mobility transition question. And there are many choices to make in the next decade, or actually very soon. So to make those choices, what kind of criteria are important to consider when we look at this energy transition in mobility? A little bit of background. The emissions of CO2 are slowly declining, but really only slowly in the past decade and a half, perhaps. On the left, you see the domestic mobility emissions, in which the personal cars are the biggest share, but also the freight sector, bestel- and vrachtauto's, for those who can understand that. The freight sector is also quite important, about 2/3 of the personal cars, private cars. But also, interestingly, mobile equipment is quite significant. But if you look in a broader way, the Netherlands has a bit of an interesting position when it comes to international aviation and shipping. Rotterdam and the Schiphol airport are big bunker fuel station, especially the Rotterdam port. So actually the emissions, if you calculate the emissions from the fuels that are bunkered for international aviation and shipping, are even higher than those of domestic emissions. These international emissions are not counted within the IPCC national accounting framework, but of course, to look at, if we want to go to a 1.5 degree scenario in the world, we have to look at international aviation and shipping as well. So therefore, we look at both domestic and international emissions from the fuel in the Netherlands, and both are very, very challenging. One step back as well, as a framework to look at CO2 emissions in the transport sector. You can use the framework developed by Lee Schipper in the late 1990s. He described it in a way called the ASIF framework. So that is that the total emissions are the product of activity in person kilometers or ton kilometers, and then multiplied by the modal split, and then by the energy intensity, so the amount of energy per person or per ton kilometer, and finally the grams of CO2 per unit of energy. If you look at those four parts, you can directly link those to policy options to reduce those emissions. And they can again be broken down into a framework developed in Germany in the late 1990s, but also recently taken up, becoming more popular also in the IPCC framework called the Avoid, Shift, Improve framework. So Avoid looks at the activity, so the first factor of the ASIF framework, to have shorter trips or less trips, that sort of approaches. Shift is to shift from one modal choice to another, so to a less energy and carbon intensive mode. And finally, the improve options, they look at only the individual modes and how can we improve the energy and carbon efficiency of that. And our study does not look at avoid and shift, only looks at the improve part. So that's a choice in the scope that we made. So in short, that means that we look at carbon neutral mobility in 2050 through carbon neutral energy chains. The modes of transport, as I said before, they are or I didn't name them yet, the private cars and vans. We take them together. The heavy duty vehicles in freight transport, road freight transport, then inland shipping, international shipping, and intercontinental aviation. So we did those based on the total contribution to the CO2 emissions of domestic and international mobility in the Netherlands. Then the scope can still be very large. There's many choices to make. So one thing we also did was we only considered those combination of energy carrier and modes of transport that have a technological development level, technology readiness level of 6 or more, which means that they need to be demonstrated at a significant, at a large scale, at the full scale already. If they are less technologically developed, we did not consider them. And another consideration is that they need to be practically applicable in the modes of transport. So, for instance, ammonia in road transport we did not consider. It's technically, of course, possible, but ammonia is toxic, and it's not very likely that that will happen in road transport. And for intercontinental aviation, we did not include battery electric or hydrogen. Because the weight and the space of the battery or the hydrogen storage will be very, very challenging. So for short distances, this might be possible, but for intercontinental aviation, we consider this unlikely to happen. One last remark about the scope. We want to explain the energy chain a little bit more in detail. We considered 4 steps. The first one is the production of the energy carrier, and also the production of, let's say, if we talk about biofuels, it's not only the biofuel production, but also the biomass production, so the growing of the energy crops. The second stage is the transportation, the storage and the distribution of the energy carrier, so the fuel or the electricity or the hydrogen. The third step is the charging or the refueling of the vehicle or the vessel. And the last one is the use in the vehicle. So this is a full well-to-wheel approach. And what we did not do is a full life cycle analysis. So the production of the equipment to, let's say, the production of a wind turbine or the production of a hydrogen tank, we did not include. This is a very simple way to look at the energy change. In reality, they are quite complex, as I will show in a bit as well. The energy change can be quite long because this energy is a global market, so they can be transported on long distances and many steps in between. They can also be bifurcated. So from certain types of biofuel, biomass, you can choose to make like 4, 5, or 10 types of biofuels. So there are many subroutes in the energy change. So we simplified them a little bit, but they're still quite complex. They're also interlinked, and that I will show in the next slide. And of course, it's an obvious note to make, but we need to realize that mobility is only one of the energy consuming sectors. There will be competition with industry, buildings, the electricity sector. So we're looking at quite a energy for mobility landscape that is increasingly complex. To illustrate that a little bit, this is about half of the overview diagram that we use, and it's already getting a little bit interlinked, for instance. So electricity is, for instance, produced, we considered from wind energy and solar energy. And it can obviously be directly used in vehicles, but it's also an input in green hydrogen production. And it's also used in significant amounts for the compression of the hydrogen that is already produced. Another important note to make is that, for instance, CO2 is an input into the Fischer-Tropsch process, which is used to produce synthetic fuels. And maybe one more remark to make here is that if we look at the electricity chain on the top right, it can in the future maybe also work both ways. So you can use electricity to charge your electric vehicle, but the electric vehicle can also be used as a storage option, and be fed back into the grid when there are reasons to do so. When the vehicle is standing still and there is a demand in the electricity grid that can be met by these stationary batteries in the vehicles, then vehicle to grid can become a reality. So this for illustration of three of the change. The biofuel chain also is obviously part of it, but I will not show it here in the interest of time. Okay, so the final part is obviously the results. So in very brief, we can say all the four chains that we consider are carbon neutral or nearly carbon neutral, but there are very strong differences in the energy consumption. With the least efficient chain, about 5 times more energy consuming than the most efficient chain. And this difference in energy efficiency has also strong implications for the costs and land use. And I will go in each of these three energy, cost, and land use in the next few slides. So first of all, energy consumption. Here we show it in a relative way. So the most efficient chain is wind energy and a battery electric vehicle. So we consider that as a 1. And express the other chains relative to this chain. So you can see that for hydrogen, it's at least twice the energy consumption per kilometer will be at least twice as high, but it can also be 4 times as high, and in certain cases also more than 4 times. The synthetic fuels. So here there are many synthetic fuels that we can consider, but here we only, for simplification, we only included the Fischer-Tropsch synthetic fuel produced with CO2 from capture from the air. So that's DAC, DAC, direct air capture. And to produce that, you need even more energy than for the hydrogen chains, partially because you need hydrogen and CO2 to produce the synthetic fuel. For biofuels, the chains are also a lot less efficient than for electricity. This is mainly because they will be used in vehicles with an internal combustion engine, basically like most of the vehicles are now. Which are really inefficient compared to an electric motor, which is very efficient. And for bioethanol, there are many steps. There are many steps that you need to in the process to produce that fuel. So also in the production process of bioethanol, a lot of energy is lost. I think this is the picture for energy efficiency. And this will translate into costs to a large degree, but of course not one-to-one, which I'll explain right now. Here you can see the energy costs for the different type of fuels. The orange and the red bars, they are dominant in most of the change. These are the material inputs that you need. So for instance, for the biofuels, the production of the biomass, and for the synthetic fuel, the costs of producing electricity and producing hydrogen. And for hydrogen, the costs of electricity. They are dominant in the biofuels and the synthetic fuels. But for hydrogen and for electricity, also the charging and the refueling steps are quite important. Another thing that is very clear, I think, in this graph, we included uncertainty bars, the small bars, and they are quite large. So even for 2030, which is not too far in the distant future, the costs are very uncertain. And these are costs without taxes and subsidies. These are the basic costs. And of course, we can see in the markets recently that it is also very difficult to predict these costs. But that's an important notion, that the costs are quite uncertain. So these are for energy distributed at the fuel station and the charging points for road transport only. And this will translate into total costs. We express it by kilometer, so kilometer by road, for passenger cars and for heavy-duty vehicles. For passenger cars, the investment costs in the vehicle are the most important for most of the energy change, and especially for fossil fuel and for electricity. The energy costs are really just a relatively small part of the total costs. But for heavy-duty vehicles, it's the other way around. For heavy-duty vehicles, they of course they have a mileage per year about 5 times of that of a passenger car, and obviously they're also a lot heavier. So the investment costs are for heavy-duty vehicles are a relatively small part of the total costs. But the picture for both passenger cars and for heavy-duty is that battery electric vehicles are likely the most economically the most advantageous option. Although for biofuels there is a very big uncertainty in the costs. So it might be that biofuels can also compete with electricity. The other fuels, like hydrogen and synthetic fuels, they are likely to be more expensive per kilometer. But again, just to highlight again, the uncertainties are quite considerable. Even though we did not include them here, they are large. So that's the cost. The third criterion that we looked at was the land use, so the space requirements to produce and to transport the fuel. This is something that we did not see addressed a lot in existing literature. So we hope that this is also a contribution to policy, but also maybe to academic discussions. And we expressed it here for how much land or sea surface do you need for the energy supply of one passenger car. So again, the electricity is the most efficient, energy-wise, the most efficient chain. So that is also has the lowest land use, but it's still very significant. So for the Dutch electricity mix, which is included in a few climate neutral scenarios for 2050. In those climate neutral scenarios, the electricity mix is about 90% is wind and solar, and 10% can be other backup electricity, but about 90% is wind and solar, and out of that, 3/4 is wind and 1/4 is solar. So that's the base. That's the basis we used here. If you look at that, then still you need about 12 square meter for a passenger car to fuel, and this is net land use, which means that for wind energy we only take the amount of land or sea surface that the turbine is occupying. So the space between the turbines is not included, which I'll come back to in the next slide. So, and for hydrogen and for synthetic fuels, because they're much more energy consuming, of course, the net land use will also be higher. For biofuels, there are two options, and we can say these are two extreme options, but at the moment, most of the biofuels used, at least in the Netherlands, are coming from residues, agricultural residues, or used cooking oil. And you can argue that to produce those, we don't need additional land. So the land use for biofuels from residues is very low. However, we are quite sure that we cannot meet the needs for biomass in all sectors by residues in the future. So we will need energy crops, like woody biomass, cellulosic biomass. And if you use that to produce biofuels, the land use is much higher, in such a way that it will not fit in the scale of this graph. But it's about a factor of 10 to 20 more than the other options. So these are the two extremes for biofuel. I'm looking at the time. Okay, so it's still 1 o'clock. So there's a few more slides. So this was the net land use. Like I said in the previous slide, the space between the turbines is not included. But obviously, we need to build those wind farms. So we also did some calculations on how would it look like if we build those wind farms that are needed to produce electricity for mobility. And in the first scenario, we looked at only road transport, and we simply considered, if you look at all the road transport currently, so that's the heavy duty vehicles, vans, buses, and passenger cars, if you make those electric, what surface area of wind turbines do we need? And it turns out we need about the province of Utrecht, that surface area to produce enough electricity. Of course, you can also do it by solar, and then the surface area will be much less. But wind energy will be dominant in the future electricity mix, so that's why we use that as a basis. On land, it might be difficult to do that. Of course, we can also translate this surface area into the area you need for offshore wind. And then it should be manageable in the Dutch situation, although still challenging perhaps. But that is only road transport. Like I said in the beginning, there's a lot of bunker fuels for international maritime and international aviation bunkered in the Rotterdam port and at Schiphol airport to produce synthetic fuels to let's say take the current amount of fuel that's bunkered in the Netherlands and that's 99.9% fossil fuel, to shift that to a synthetic fuel. You need a surface area of wind farms that has 9 times the province of Utrecht, or that actually corresponds quite well to the total potential for wind energy on the North Sea, of the Dutch part of the North Sea. So this is a very big challenge. And by comparing the road transport and the international aviation, there's one thing, again, that's very clear. It's the energy efficiency aspect. So for road transport, if we go from the current scenario to electric, we will gain, the energy efficiency is at least 3 times better than the current scenario. But for synthetic fuels, it's less. Synthetic fuels, to produce them, the whole chain is less efficient than the fossil fuel chain right now. So this bunker fuel question for the Netherlands is a very big question. Instead of synthetic fuels, we can also have the scenario that we use that we produce it by biofuels, the bunker fuels, and then the surface area needed is even bigger. It's about 0.5 to 3 times. Let's say on average 2 times the surface area of the Netherlands if you do it from biofuels from energy crops. So compared to synfuels, for biofuels, you need even more surface area. Okay. This is the These were the three main aspects that we look at. We have a few, of course, these are only three criteria: efficiency, costs, and land use. But there are many other things to consider when we look at energy change. So we have a few examples here. For electricity, which means that it's also partially relevant to hydrogen and synthetic fuels. A few of the barriers are the available of materials, so rare earth materials and metals like cobalt, nickel, and lithium, but also, for instance, copper. We need a lot of copper for the energy, for the whole energy transition. Recycling, especially of the batteries in electric vehicles, is a big challenge. Steps are being made, but we're very far off 100% recycling of batteries. In the energy transition as a whole, electricity will play a very, very big role, one way or the other. And to accommodate this, the electricity grid needs to be expanded and also enforced. And some reports in the Netherlands say that we need 4 times as much investment in the next 2 or 3 decades than we have invested in the past decades. And apart from money, it needs to be done too. So you need skilled technicians, and there is a significant lack of these. So there's also a technical capacity issue. For hydrogen, other than that the barrier is that they need to be produced from electricity, and that we have the issues that I just mentioned. A specific issue is that when we look at fuel cells, it's not known well yet how much these fuel cells will be degrading over their lifetime. It could be that within a few first years of their lifetime, the efficiency goes down quite significantly. It could also be that they are very stable over their lifetime, and there is a lack, at least to our knowledge, there is a lack of research and experience in this. When we look at synthetic fuels, of course, the big advantage is that with very little adaptations to the existing fuel supply, you can use them in transporting them and in using them in the internal combustion engine that we have now in different modalities. That's a big advantage. But especially for ammonia and methanol, these are toxic, so there is a safety issue. For biomass of biofuel, actually, these can also be used with very little adaptations in internal combustion engines as the big benefit of that, but they need to be produced. So residues will be significant. They can be produced and brought to the market in quite a significant flow and cover a certain part of the demand. But we will also need energy crops, which is a big question. Are they? Where can we do that? And do we have enough land to do that? And can we do that in a sustainable way? This will depend very much in which country you would look at. In the Netherlands, I think there's relatively little land available, but maybe in Sweden, there is already a big economy around producing energy crops. So land availability needs to be explored further, and we see a very big range in literature on what is the potential for energy crops for producing biomass and biofuels. So the availability of both residues and energy crops is quite uncertain. So to conclude, out of the 4 carbon neutral energy change that we considered, the one based on electricity is the most energy efficient, and the electricity chain for road transport at least, is also likely to be the lowest cost option. Although we have to say that uncertainties are quite substantial. One important aspect to look at, I think that our report has shown that, is the land and availability of surface on at sea to produce the different energy carriers. So the land required or the sea area required is substantial. So this is something that needs attention, especially in policy circles. It will not be the same for every country. For Netherlands, this is definitely a very big issue, especially because we can see that for carbon neutral bunker fuels, it is very simple. It's not possible to do that domestically. If we would do that, it means there is no carbon neutral energy for other sectors available. So energy imports will be required for sure for the bunker fuels. And then in general, the energy transition in the mobility sector will have, there will be a certain dynamic in international and global markets. So imports is going to be part of the puzzle when we look at energy in carbon neutral mobility. So that's it from my side for the presentation.
Thank you very much.
And I'm happy to
take
questions.
a big applause. So if you have questions, please raise your hands that I can see them. Then we can assign who asked the questions. So are there already any questions so far? Maybe I can start with a delicate question, with a question of the devil's advocate. From your study, can I conclude that either we need other energy sources than the ones typically considered, or that we need to increase the dependency on other partners, on other countries, to be able to make the energy transition?
Thank you. That's of course a very interesting and important question. I think there will be many debates about that. There are many criteria to consider when we look at energy for mobility. And for the different modes, these questions might also be slightly different. I think in the road transport, for sure, private cars, but I think also in heavy duty vehicles, at least in Europe, as I can see, there is a trend towards electric mobility. Be it via fuel cells for heavy duty vehicles or not, but that's an electricity question. Yeah, so for at least for a country like the Netherlands, where we have quite a high population density, combined with a very big bunker fuel market, it will not be possible to solve the energy puzzle, the carbon neutral energy puzzle 100% domestically. So yes, imports will be required. But how to do those imports? There can be direct import of electricity will be, of course, I think limited to the Western European market. But hydrogen can be transported. Also synthetic fuels or biofuels, they are a little bit easier to transport. There might be all kinds of technical, economic, and also political questions around that. But somehow imports or international markets for energy will be very important, I feel.
So in the meanwhile, if anybody has a question, and you can raise your hands, and then I'll happy. Yeah, Emanuela.
Can you hear me? Yes.
Yes.
Yeah. Okay. So I'm Emanuela Peduzzi. I'm from Transport and Mobility Leuven, and I liked your slide with the land use and the different types of fuels. And I was wondering, I think for biofuels, you put there Fischer-Tropsch fuels, but in the previous slides, you had bioethanol. So I think there it would be very, I wanted to see also the bar for bioethanol, because there you see if it's bioethanol made from crops, from agricultural crops, there the land use really enters into competition with food production. So I just wondering if you have an idea of that, how that bar would look like on that graph.
Yeah, thank you for that question. We did include bioethanol as well. In the report, it's there. For the presentation, I didn't want to make. We have about twice the number of bars as I showed in the presentation, just to keep it manageable. We did not consider bioethanol from, let's say, the first generation ethanol from sugarcane or corn, but we included cellulosic ethanol. So from the top of my head, the bar compared to the one I showed for Fischer-Tropsch, I think the ethanol is a little bit more, but it's in the same order of magnitude. But I'll have to check in the report how much it was, but it's kind of similar. I think if you would do it for first generation ethanol, it might be lower because the production process is a bit more efficient. But of course, that competes with food crops. So for that reason, we did not include them, because it's also in the Renewable Energy Directive. I think they are not part of the biofuels that are considered for 2030 and beyond. The Annex A of the renewable energy.
Yeah.
They're still included, but they are supposed to not increase. And the second generation biofuels, they are supposed to increase. So we only consider second generation biofuels.
Okay. Yeah. Thank you.
Thank you for your question, Emanuela. Any other question? One that I'm wondering at is, you focused now solely on the improvement aspect. Did in your analysis also did broader and look at the shift or the avoid part in the potential actions?
The short answer is not yet. So we simply looked at only really the fuel carbon content and energy efficiency implied in that, because electricity is much more efficient. Avoid and shift, we also think that will be an important and probably essential part of the mobility transition. I think also the latest IPCC report has put a lot of attention on those more behavioral aspects, and in freight transport there are options to improve the load factor, for instance, and to shift from road to rail or waterborne transport. So there is definitely a potential, but we did not yet look at it. We are going to look at it in the next this year and next. Well, this year is almost over, but in an upcoming project we will be looking into those. And one of the reasons I do think the current published report does show that saving energy is always the best option. You don't only save energy, but you save costs probably, but also you need less land to produce those energy carriers. You use less scarce materials. So in terms of land use, any material use, saving energy for sure has a benefit. On the other hand, I must say, when I read the IPCC report, I did find them a little bit optimistic. I think the conclusion was that across all sectors, not only mobility, but all sectors, behavioral and lifestyle related measures can be 40 to 70% of the solution. I am not 100% sure whether we at KIM would subscribe to that that conclusion, but it can definitely be a part. But it would be very interesting to look at it for all of the different modalities, because, for instance, in private cars, there might be certain options. For instance, working from home is a kind of a big thing. So that will have an impact on perhaps on private car use. But for aviation, there's very, very different kinds of considerations. And then within aviation, there is let's say the trips that are taken for private purposes and the more business related travel. And the potential in business related might be very different from the private transport. So I believe this is definitely a very interesting and important part of the whole question. And I think for research-wise, there is still a lot to gain in that. We can also see that in the ministry. There are several policy actions related to avoid and shift measures. But if we look at the potential and the expected CO2 emissions we can gain from that, the uncertainty bars are quite large. So from both a research and a policy perspective, this is definitely very interesting.
Okay, thank you very much for your question. One final look at whether there are still some questions by the audience. You don't see any hand anymore, so thank you once again, Stefan, for your very nice presentation. So the presentation will also be made available through the BWKIBET website afterwards. Once I edit it, I will send you also a confirmation mail that you can have a look at the presentation. So thanks you once again for your presentation. And I look forward to seeing you all on the 7th for the second lunch talk. Thanks again for participating.
Thank you, Mario, and everyone.
Bye.
Bye.